Texas Medical Branch Medical School, completing 2-year surgery internship and residency at Johns Hopkins Hospital. After that, he completed a 4-year residency in ear, nose, and throat surgery at the University of Michigan and was board certified in otolaryngology. In the early 80s, he became interested in allergy, and the need for a therapeutic approach to treat children with allergies sparked his initial interest in homeopathic medicine. I even had my grandson see him several times, and for a difficult ear problem that he had. Since then, he's been using low-dose natural combinations to treat allergies in both children and adults. And an interest in chronic diseases led to the further study of homeopathy, and to document knowledge in this area, became licensed in the state of Nevada as a homeopathic medical doctor in 1986. And I'll leave the rest for him to tell you. I introduce Tim Guilford.
Thank you very much. I guess I've done a lot of things in medicine. I've been a bit of a vagabond through medicine. But I realize now that it was all in preparation for getting ready for glutathione, because glutathione is plays such a key role in so many problems. One way to look at it is, I read in the New York Times recently that about the recent surge in movies that have interlocking plots to tell a story, because one linear storyline won't give you all the background that you need to understand what's going on. And I think glutathione actually will play the key role in the interlocking plots of many diseases and organ systems. It's interesting, people want to understand about the organ systems, and that's the way medicine's been organized, because that's what was obvious when you look at it. There's some common mediators that influence all the organs, and of course vitamin C is one that we've heard about a lot, and I'm going to try and explain the role that glutathione may play. And this story actually starts way back in the early evolution of cells. That blue-green algae that's on the surface of the water at Hetch Hetchy played a big role in creating the need for glutathione. The cells that existed 2 to 1.5 billion years ago began using sunlight to generate their energy, and produced oxygen into a world that was predominantly covered by a CO2 environment. So the cells were able to live in the CO2 environment and go around and grab other objects to eat and survive. But the oxygen that was being produced by the blue-green algae began to create an oxidation stress environment that created problems for these organisms. And this is the oxygen crisis that we now live in as beings in this world now. And the mitochondria played a key role in allowing the cells to survive in that environment. This is probably the longest running partnership in existence, at least from the point of view of the eukaryotic cell, because the mitochondria allows the cell to utilize oxygen. It's a complex mechanism called oxidative phosphorylation, but it's really kind of simple. A lot of the cycles that you learned in school bring electrons to the mitochondria, and they are in a high energy state, and they go through a series of proteins that allow the energy to be released slowly and recaptured to take ADP and form ATP, the energy packet that our cells use. In the process, then, at the end, the spent electron is released into, and this is the key, broken down and utilized to form harmless water and oxygen. So, or the oxygen is converted using the electrons to form water. This is fairly efficient, but not perfectly efficient, and so some of the electrons are blasted off and create free radicals, and this is the origin of the term reactive oxygen species, or free radicals, that we all hear about, and that's what you need antioxidants for. And even that 5%, though, can be dangerous to the mitochondria when it was floating around in a free water environment as a separate living entity. It could release these electrons without any problem, but inside the enclosed environment of a single cell, these free oxygen radicals became dangerous to the cell itself and also to the mitochondria because they disrupt cell function and things just quit working is the bottom line. These radicals are often expressed as singlet oxygen or the hydroxyl radical, and it turns out that the cells that were able to produce glutathione created the ideal environment to allow mitochondria to exist. Now, vitamin C, vitamin E, all of these play a role. Vitamin E in particular because it's a water-soluble antioxidant, vitamin E because it's a fat-soluble antioxidant, and glutathione kind of plays a dual role in there, as we'll see. So the high-affinity transport of glutathione is part of the multi-component system that's essential for mitochondrial function inside our cells. And this is because the role of glutathione is a little different because it is able to interact with some enzyme systems, particularly the peroxidase, glutathione peroxidase, which transforms the hydroxyl radical, see if I can point that out, the hydroxyl radical, the OH, back into harmless water. And that turns out to be a key element in the whole process because the hydroxyl radical is one of the stronger of the radicals as opposed to a single oxygen radical, and it will cause a great amount of damage. And what happens with oxidation stress is it just goes like a cascade, like those ping pong balls in the old Walt Disney display of a nuclear reaction. It doesn't stop, it just keeps going in a cascade fashion until an adequate antioxidant is encountered. And so a free radical will turn a normal protein into a radical itself, disrupt its function, and go on to disrupt the next protein until an antioxidant is encountered. And that's why in certain situations you need large amounts of antioxidants. Well, let's see. Here's glutathione in what's called the reduced state. That means it's got available electrons to donate that are coming off of this sulfur group over here. And here it is in the oxidized state in which two glutathiones have combined together through a double bond at the sulfur groups. And the key here is that when vitamin C comes along or another antioxidant, these can be separated and go back into a functional state. Most proteins, when they're radicalized, if you will, damaged by oxidation stress, oxidized, they can't go back to normal function just by adding an electron back in. It gets really messy. They have to be broken down and reformed, and that takes a lot of energy for the cell. And here's the depiction of the interaction between these, what I call the trio inside of the major orchestra of antioxidant function. And each one of these going from an oxidized state back to a reduced state and so forth, keeping each of them in an active functioning state. That's vitamin C, vitamin E, and glutathione. So everybody wants to know, how can you make glutathione? It's relatively simple for your body to do it. We're going to get into that and the complexities of that. But the glutathione itself is 3 amino acids, glycine, which is found in all foods, glutamine, found primarily in proteins, and cysteine, which is more highly represented in certain food groups like egg yolk. Although it's present in all foods and all cells, it's at too low an amount to really replenish the formation of glutathione when you're deficient. So here's the cysteine, which has the sulfur group on it, and it's in the center of the glutathione molecule. Glutathione can be transported either as two pieces of the three, the glutamyl cysteine, that's the glutamine and cysteine combination, into cells where glycine is added along with a little antioxidant. You form glutathione itself. There's also some conduits that are becoming better known, such as the transmembrane conductance regulator, CFTR, receptor that carries anions such as chloride into the cells, will also carry the whole glutathione molecule. And this type of transport may play a big role in getting glutathione in kind of a fireman-like response to sites of inflammation and stress. because inflammation is roughly equivalent to oxidation stress, as you'll see, and needs a lot of antioxidants to calm this down. So here's the sources of these amino acids. The cysteine is found in egg yolk, and some people say you can eat a lot of eggs and get this, although you have to remember that you're going to change that amino acid when you cook it. The glutamine is found in meats and high-protein foods, and these are the two elements of several things that are missing in vegetarian diets. I have no philosophical problem with the vegetarian diet, but practically speaking, you're missing some key elements because the cysteine is found primarily in the protein, especially the egg. The glutamine is found in protein, especially meats. And you can become deficient in either one or both of those and not make enough glutathione. And the third factor, of course, is B12, which we're going to visit a little bit at the end of all this. So I tell my friends or clients that I see, if they're vegetarian, the importance of taking something like N-acetylcysteine and glutamine every day, unless you're really careful with the way you eat. And the reason is that kind of diet is really successful in a non-toxic world. Because a vegetarian diet is low in creating oxidation, but we don't live in a non-toxic world. We live in the reverse of that world. And it's getting tougher all the time. It seems illogical almost. So anyway, cysteine is the rate-limiting factor in the production of glutathione. So you can take things like N-acetylcysteine, which you can buy at the health food store in quantities of 500 or 1,000 milligrams a day without any problem, and help maintain your glutathione as long as you're eating a well-rounded diet, including protein on a regular basis. Some of the areas that begin to show that glutathione is needed in certain spots more than others. For example, the liver makes 7 times more glutathione than other cells, and that makes sense because that's a site for detoxification. The glutathione is then exported to the plasma where it's carried to other cells. All cells make glutathione, but when you need more, the body can carry it there, it appears. And as an example, you need glutathione to get your bilirubin to be formed and to be moved out of the liver. So it shows you the importance and the role of this in example after example. We're going to talk. Bilirubin's the stuff your liver makes that goes out into the gallbladder. It's called bile, that sort of thing. It's a dark colored material that causes your stool to look dark. So if you don't make bilirubin, if you have liver disease, one of the first things the doctor would ask you is, have you had light colored chalky stools? You're not making enough bilirubin. Does that make sense? The exception, some of the cells in the brain don't make glutathione. They actually have to get it from adjoining cells. And this big exception is a neuron, and that begins to explain some of the problems that we see in neurodegenerative diseases. So we've talked about one function. Let's talk about glutathione as a detoxifying agent. Mercury is a favorite topic of mine. And it should be a favorite topic of yours because it's another one of these things that's ubiquitous in the environment. It's an equal opportunity toxin. It is even in the air from coal-burning generation plants and probably petroleum and things like that. Well, an enterprising group asked the question, where are these toxins stored? We know they're fat-soluble, but what part of the cell or what part of the fat do they show up in? And so they took non-lethal doses of mercury, low doses in other words, and gave them to cells that were derived from liver and into a cell culture, and then later took the surviving cells and broke them up to see where the mercury was located. And the intriguing thing about this is that while the cell wall seems to quite large, only 15% of the mercury was found there. In the nucleus, they found 35% of the mercury in the cell wall, the nucleus, nuclear wall. And, however, the mitochondria actually had 45% of the mercury. And I think this begins to explain a lot of problems that we've seen. When you get a material like mercury into the mitochondrial system, you begin to disrupt cell function more readily because you're creating more free radicals much more rapidly. And so getting rid of the mercury, and it would make sense, diseases like chronic fatigue, or it really makes sense with any disease, that you would have an accompanying fatigue that's compromising some of the function of the mitochondria, but especially in diseases like chronic fatigue and a lot of the chronic illnesses we see. I have seen mercury play a role. And to me, when you have elevated mercury, you're going to have the potential for deficient glutathione, and I believe that that equation goes in two directions, because glutathione is the primary way in which mercury is removed from the body. Our body ran around in an environment where it was growing up, where it spent more time acquiring certain minerals like iron, but it did not need to develop a way to get rid of iron. I keep moving around for the camera there, sorry about that. I'll come back into focus from time to time. So there's really not a good exit strategy for metals. There's ways the body really regulates the iron stores, for example, by when they're adequate, it doesn't bring in more iron, because it really didn't run into a problem of accumulating too much over time. So glutathione can bind the mercury and pull it out of the cell, creating a water-soluble complex from a previously fat-soluble complex. And that's the real key role of glutathione in detoxification. It creates a water-soluble complex that can be excreted primarily through the liver, back to the bilirubin, out of the body. Does that make sense? It turns out that oxidation is a tremendous cell signal, and this has to do with regulating immune function, for example. And it's not well understood or utilized yet in clinical medicine, but there's good basic science evidence to demonstrate that if certain cells involved in creating the immunologic response are low in glutathione, you will get a preferential movement of the mechanism towards what's called the chronic inflammatory response, which is also known as the Th2 response. Th1 T cell, T helper cell, primary response. That appears to be, to me, the major way the body defends itself. Something comes in, the body doesn't want it there, it doesn't recognize it as normal, it engulfs it, and it kills it and removes it. The killing mechanism requires either the formation and utilization of oxygen radicals or nitrogen radicals. So we now have reactive oxygen species, ROS, and reactive nitrogen species, RNS, and the nitrosative reactions are used in killing to a great deal inside the cell, such as T cells, natural killer cells, and that sort of thing. These cells won't upregulate those mechanisms if it doesn't have enough glutathione available. So what happens is you default to the secondary mechanism, which is producing antibodies that are used as part of the alert mechanism. They wall off and hold off inflammation and invaders, but they create a constant battle. They don't get rid of the problem, and so the problem will go on, and that's what's called inflammation. And chronic inflammation comes in when this inflammatory mechanism becomes deleterious, becomes negative or damaging to the body. That's what chronic inflammation is. And to me, I got started with all this looking at allergy. I couldn't figure out, why does the body have a mechanism like allergy, which is very efficient or very effective at creating a big alert mechanism and that sort of thing, but it doesn't solve the problem, and it's not getting rid of it. I mean, the things that they're attacking, like the antigen materials, aren't even necessarily harmful. Well, it turns out if you have low glutathione, they can't upregulate the oxidative and nitrosative mechanisms to break that down and kill them, and so it just keeps that mechanism going on. And clinically, in my experience, when you raise the glutathione level enough, you can manage a great deal of those type of allergic, so-called allergic symptoms. It's really quite fascinating. And here's a publication from 1994 that is essentially saying this, and I put the quote in here because it's just too cool. Glutathione reverses the inhibition of T cell responses. I mean, it's got a bunch of double negatives in there. By superoptimal numbers of non-professional antigen-presenting cells. Antigen-presenting cells are the first link in this chain of presentation. They're macrophages and dendritic cells. They grab things, they take them back to the lymph node where a committee decision is made. What are you going to do? Well, if you present it with low glutathione, the committee always says, go to chronic inflammation, because we've got T cells out there, but they can't work. They're non-professional. That's what that term means. They're not working. And so glutathione will reverse the inhibition. They've slowed their function down because they don't want to get rid of all the T cells. Our body, we used to think that these cells went out and destroyed things by suicide bombing. They don't. They're part of a very intelligent system, and they go out and sample and bring back and interact, and they're well trained, but they're also taught not to engage these systems if it is self-destructive. It's really quite fascinating, the parallels from the inner world and the outer world. In my personal, to me, it's just a whole big chain up and down from the inside to the outside to the way we're thinking, but that's another story. So what kind of diseases have low glutathione, if we're going to talk about that? These are all referenced diseases. I left off aging because that sounds like it's too big a catchphrase. But there's an article that shows that chronic illness and aging are characterized by low glutathione levels in the blood. Incidentally, the reason you don't see people offering you glutathione studies, I do in my practice because I've found a lab that does pretty reasonable, very reliable or reproducible testing. But it's very controversial because just taking the blood sample, putting it into a test tube, exposes it to oxygen and a lot of stress, and so you use up the available reduced glutathione. You end up with a lot of oxidized glutathione, and so you get into this huge controversy about the meaningfulness of the testing procedure itself. And unless you freeze the sample within a few minutes, you actually have to add an additive first to negate the progression of these reactions. So here's some diseases you've probably heard of. Alzheimer's disease. Men with Alzheimer's have actually been shown to have lower levels of glutathione, and particularly I believe it was glutathione peroxidase, the enzyme associated with the function of glutathione. A lot of times when you read studies related to glutathione and minerals and that sort of thing, you'll see discussions of selenium. Selenium is an important cofactor for that glutathione peroxidase system, and it's almost so important that some people believe that if you're low selenium, it's the equivalent of saying your glutathione peroxidase is not working properly. So that's where selenium comes into this mechanism. Anyway, I believe it was the Alzheimer's patients, the men particularly had lower levels of glutathione peroxidase in their system. But just giving glutathione to a patient with Alzheimer's doesn't appear to solve the problem. We're going to talk about a couple of things that do appear to respond, however, to replacing glutathione. Diabetes has a lot of oxidation stress, and that's probably where a lot of the vascular problems related to related to diabetes comes in. And there's a whole literature on that popping up. Viral disease, both chronic and acute, have been associated with depleted glutathione. Petri dish studies, and if we have time we can go into the discussion that I gave part of, the panel discussion on viruses and the role that glutathione may play there. But if we don't get to it, I want to be sure and mention the fact that glutathione can be very helpful in treating viruses. So let's talk about some disease states, and to understand that we have to understand that glutathione can be compartmentalized. That means you could draw a blood sample and find out what the glutathione level is, but it may not reflect what's going on in some other parts of the body. And that's illustrated by a study that has shown that they took patients before and after surgery and did a blood sample test and a muscle biopsy test. So they had nice volunteers. This was done over in Sweden. It's a little tougher to do those invasive kind of routine things over here, I guess. But anyway, before abdominal surgery, they ran those two studies, and they showed the plasma, meaning the blood level, was normal, both pre and after surgery. The muscle level, however, dropped over 40% after surgery, and that implies that the body needs to maintain glutathione in the blood at a certain level, and it will rob it from other sites, if you will. It uses other sites as a reservoir. And that can explain why many people with overtraining and things like that can use up the glutathione in their muscle and begin to run into problems, and that's fairly well documented also. The same thing, incidentally, can happen in the brain with certain diseases. Certain diseases have been shown to have actually low levels of glutathione in the cerebral spinal fluid and an elevated level in the blood, and that can create a lot of confusion. in explaining, and I don't have a great explanation for that yet, but the specific disease that's been documented is multiple sclerosis. It's really quite fascinating. So if you drew a blood sample on somebody with that problem, you could actually find an elevated level of glutathione and assume that that's not the problem, when it's just the reverse. Parkinson's disease has a deficiency of glutathione localized in a certain portion of certain cells in the brain. And these cells are called the substantia nigra cells because they stain dark, and that's where the nigra comes from. And that's part of the body is where dopamine is produced that is then sent off to the neurons that have to do with muscle function and muscle coordination. And loss of dopamine through oxidation has been demonstrated to be one of the major mechanisms in Parkinson's disease, and that's why people are given dopamine-enhancing medications to take to overcome that problem. The first, in experimental models of Parkinson's, the first thing that they measure changing is a decrease in glutathione. So it's documented to have low glutathione in those cells. So that should be simple. Let's give them some NAC and raise their glutathione, make sure they've got some glutamine. You can do that with whey proteins, for example. So those two things didn't seem to give much change. But if you give glutathione intravenously, you can see sometimes a very rapid improvement in some of the symptoms related to Parkinson's disease, either the tremor and or the coordination of muscle movement that is lost with Parkinson's. The problem with the IV, of course, is it doesn't last forever. There's actually a study in which they gave about 10 patients 1,200 milligrams of glutathione a day to 600 twice a day intravenously for a month. And then we're able to document a 40% increase in the improvement in the Parkinson's symptoms. And this lasted for about 1 to 2 months, and then whatever the underlying mechanism that's causing Parkinson's caught back up to them, they became depleted in glutathione and their symptoms came back. There's the reference, and there's the numbers. I think it's really intriguing that they stayed better for 30 days, or after 30 days they stayed better for 1 to 2 months. I mean, it's brings up a lot of the mechanisms, a lot of consideration about the mechanisms of these diseases in general. So what happens, I think, is that tissues exposed to oxidation stress are susceptible to damage. What diseases, or what organ systems would you think of first with oxidation stress? Anybody want to? It's a real simple, it's not a trick question.
The lungs.
How about the lungs? Yeah, that's where your major interface is with oxygen. Well, it didn't occur to me until I'd seen a few patients with some other problems, but also your gastrointestinal tract is exposed to a lot of oxidation stress. You have to burn your food to use it. You oxidize it to use it. You're pulling those electrons out of the food to make it available as these things are broken down. So that's a site of high radical stress. So the sources of oxidation stress can be from inside the body, the metabolic functions, or from outside, back to our analogy with the great oxygen crisis. Oh yeah, what did I do here? Okay, so that's the answer to the question. The other thing I wanted to point out is that one of the things that stimulated me down this road was an article back in 1995 that showed that mercury, the first thing that you can find related to mercury exposure is a decrease in glutathione. Now, coincidentally, if you deplete glutathione using some chemicals that are known to block that mechanism, you can salvage the system by giving enough vitamin C. And so giving vitamin C will stabilize the system, help regenerate what glutathione you have, and do a lot of other beneficial actions. But it points out the important interaction between those two antioxidants. So the lung and the GI tract would be two areas that you would think of as being susceptible to stress. So let's look at some lung studies. And there is research that's now coming out that suggests that the site and the characteristics of the inflammation response may differ in different lung diseases, but they're all characterized by the recruitment and activation of inflammatory cells that lead to an oxidant imbalance, an excess of oxidation. So what they're saying here is the beginning of the understanding that when you have inflammation in the body, you have excess oxidation. And the reverse is true too. If you just make a body oxidized, you're going to have, call in inflammatory cells. This is part of the way the defense mechanism works. And this is another assertion to that effect, that low glutathione increases a pro-inflammatory signal, leading to further release of cytokines in the lung epithelium, the alveolar, those tiny little air sacs in the lung. And so you see some chronic inflammatory diseases here. We've got asthma, chronic obstructive pulmonary disease, severe respiratory distress, and cystic fibrosis. And in the studies, the glutathione is, here's your control. These are a compilation of different studies. Here's the patient's finding, and with pulmonary fibrosis and what's called acute respiratory distress syndrome, you see huge, here's a stable normal person, and here's somebody undergoing respiratory distress. Now this is the amount of glutathione in the epithelial lining fluid, endothelial lining fluid, ELF, the fluid that they can aspirate going from the outside to the trachea into the lung, not the cells, but the fluid there, which reflects what's going on in the cells. So you get very low levels. You also get low levels in cystic fibrosis. The asthma data was very confusing, and perhaps we can explain that in just a second. So let's look at this, some of the additional data. Here's the sources, the references for this information. I can go back to that or leave it up if anybody wants it. Okay. You ready to go? Okay. So, all right, so what happens when pulmonary disease in people that smoke, what happens initially is that you get a decrease in glutathione that is then followed by a rebound rise. And I think this is important to understand, because this is what happens when you get an oxidation stress in your everyday life. Let's say you get behind a big diesel truck, you're stuck there for 10 minutes in a tunnel. You're getting a lot of things that will stress your oxidation system, and it'll lower your glutathione initially, but then you'll ramp up, you'll signal the production of glutathione, so you get a secondary rebound rise. And the activation rate is controlled by this enzyme that sticks glycine onto the other two components. And if that gets messed up, then you can't make glutathione as rapidly, and that's the point of this article. Oh, I can go forward easily, but going back is, there you go. So here's what happens on a graphic level. Here we have somebody, and this takes a second to understand, and I'm going to move away. Here we have someone who doesn't smoke, and then, so they have what's called a normal level. I mean, this is in a normal environment, a normal person. And you start smoking, well, you're going to upregulate the production of glutathione. And that's going to happen for a while until things start to change. And if you get chronic obstructive pulmonary disease, which is a common sequelae of smoking for long periods of time, your glutathione level will be lower than it was before. And I think that's significant. It's still high, but it's dealing with such an ongoing stressor that it can't cope, and you're beginning to get changes in your cells. And then when you get a severe episode of difficulty related to chronic obstructive disease, it's kind of like having an asthmatic episode. It's very much like that. Severe stress, you actually get much lower levels. So if you compare this to someone who's normal with unstressed, the lining fluid in the lung doesn't look like it's lost all that much. But you have to take into account that it's got a huge amount of oxidizing things going on that would require a much larger amount to remain stable. Does that kind of make sense? It takes a little while to go through, but then it's kind of like one of these ahas, well, no wonder. And so here you have somebody who's very ill. They've actually begun to mount a response. If you just look at the fluid in their lungs, but their cells are being so severely damaged, they're no longer surviving well. The alveoli are not expanding properly. They become thickened. They become edematous. They're losing fluid. You're not moving oxygen into and out of your cells as readily, even though your system is trying as much as it can to stabilize that. So what happens is that this explains the mechanism that leads to inflammation. I'm not going to try and go through all of this at this point, but the bottom line is, here's yet another study that shows increased levels of neutrophils and cytokines, the hormones that our white blood cells use to talk to each other, the immune system, are upregulated in favor of inflammatory mechanisms. And without adequate glutathione, the conclusion of this study was that you get increased peroxidation. That's the word that they use to connote rusting of lipids. That's the oxidation stress on a cell membrane, or the lipid membranes that are inside our cells. So let's look at some other diseases that might have low glutathione. And the impairment of intestinal glutathione shows up in people with inflammatory bowel disease. And another place that it shows up is in these children that are born with a defect in the protein that carries glutathione into and out of cells. And that's where we're back to the fact that you can't get glutathione to the sites where you need it in that disease. And so they end up with problems in their respiratory system and in their gastrointestinal system. Now, ironically, they don't end up with brain problems. We're going to visit another childhood disease in a minute that shows up primarily as a brain problem. But they're able to make glutathione in the cells, they just can't transport it to the emergency sites when they need it. Does that make sense? So let's look at their red blood cell glutathione when they're getting really sick is low. The plasma, the clear blood part, stays normal. I'm not quite sure how to explain this in other situations, but in children with cystic fibrosis, it's really obvious. They can't get glutathione in through those membranes, even though the liver is making it and pumping it out. So the way that you could try and treat those people, you can use NAC, or you could use whey protein, and there have been some isolated reports of benefit with those things, just raising their glutathione in general. IV glutathione, I don't know if it's been tried. Theoretically, if you've got enough in your plasma, if you can't get it in the cells, there's no reason to pump it in IV. They have used and do use glutathione in a nebulizer so they can get it into the lung itself. But recently we've had the opportunity to use a liposomal encapsulation of glutathione, which is essentially a liposome's an essential fatty acid that's kind of like a cell membrane that allows the importation of glutathione, reduced glutathione into the cells. And here's a patient whose glutathione was low beforehand, and after using the liposomal glutathione for about a month, went up to higher than normal. The range is 200 to 400. The plasma went up a bit. Here's another child. That child had lung presentation. This child has gastrointestinal presentation. And this chart shows that she had pretty normal growth up until about the time she was a year old. And then it began to taper off. She went from 50% to 25 percentile growth just because she stopped growing. And then started on the oral liposomal glutathione. She had used NAC all along here. This is N-acetylcysteine, and here's where she started liposomal glutathione, and her growth rate went up to 50 to 60 percentile within 3 months of starting the liposomal glutathione, and has stayed in this pattern for over a year now. And both of these children have the remarkable experience of having almost no problem. Children with cystic fibrosis, I visited one of the best-known clinic in the country in Minnesota to talk to them and see what kind of problems people had with cystic fibrosis. And this fellow, Warren Warwick, the doctor there, has been the head of this clinic for 30 years, and he's the fellow that introduced the concept of shaking things up in the lung to get rid of the mucus. It occurred to him, well, let's take care of the mechanical problem first, and just clearing the mucus in these children extended their lifespan to almost normal. But even in the best clinic in the country, you sit there and you listen to these kids come in and they sound like they have pneumonia. I said, he let me listen with his special stethoscope that he's devised. And I said, Dr. Warwick, it sounds to me like this child could have pneumonia. And he says, oh, this is normal. And they're maintained on antibiotic constantly and that sort of thing. When they get sick, they end up in the hospital. These two children have had none of that. You examine their lungs, they're normal. They have normal bowel function. the other intriguing thing is that when these moms have learned when they get a little cold or a flu, they increase their glutathione level, but certain viruses will not really knock them down. Certain viruses do something that increases the demand for glutathione, so they have to go on like 3 times as much. And that happened, we've learned that for this one child with the lung presentation. She got sick with a flu, and they took her to the hospital, and just automatically with CF children they're put on antibiotics, but her lungs were absolutely clear, and they had not changed in their x-ray findings in a year, but that's part of the protocol. And what happened with this kiddo is she got constipated severely, and that became a problem until the mom finally pushed her glutathione level up to about 3 times normal, and then all of a sudden that cleared up too. So it begins to show you the different areas and the impact that these things can have. But the second child just had a little virus, and the mom went through the same protocol and did not end up in the hospital, did not end up on antibiotics. It's really quite remarkable. And I didn't understand this disease the way I do now. Serendipity sent me these 2 children, and I guess it was kind of just the way it was supposed to be. Through this lab that I use in the Midwest, a very small lab. It's really kind of interesting. Anyway, so it's been a real exciting experience. But why does a liposome work, and what is a liposome? It's the key to it is the fact that you have an outer membrane that's fat soluble and an inner membrane that's water soluble, so that it will hold and maintain water soluble materials like glutathione. And the other neat thing about it is that it keeps oxygen away from the glutathione, so it doesn't become oxidized. It stays in the active state, which is reduced. And you can have a single layer liposome. There's going to be more and more stuff about liposomes. It's already an exciting field, but you can have single layers, and the ones that are in this particular mixture are both single, and most of them are multiple layers. And this is what they look like if you were to freeze them and fracture them. You can see these layers of the multiple layers of bubbles, if you will, that are enclosing the glutathione. And the other intriguing thing about liposomes is that they work by binding to the cell and fusing to the outer cell membrane and letting their material go into the cell directly. So this can happen several times in a multi-layer liposome. You can go into the system, into the cell, and possibly into the mitochondria itself. It's really quite an interesting area to explore. So I've had the opportunity to give to use the liposomal glutathione in several patients that had had improvement after IV glutathione, and they were able to maintain the improvement that they had seen. This is not going to happen in every case, but it has happened, and it happens with some regularity. And it seems to be dependent on giving enough of the material to get into the system. So again, here's a documented article relating glutathione in many disease states, including neurodegenerative diseases. And one of the more prominent ones that has come up recently is a year ago this month, a woman named Jill James and her team were able to study first 10 children with autism and compare them to 10 normal children. And that's quite an enterprise, because you have to get the parents to bring in a normal child volunteer to get their blood drawn. She's subsequently done another 75 and 90 of both children and controls, and they corroborate her initial finding of impairment of a cycle in the body called the methylation of methionine cycle. Well, if I haven't lost you before, here's my chance to lose you. If anybody wants to take a nap, I'm going to talk biochemistry for about 5 or 10 minutes, and I'll wake you up when we're through. You want to do that? Are you eager for the biochemistry? Huh? Okay. All right, bring it on. All right, so what happens in this cycle is methionine, which is a normal amino acid or an amino acid, is utilized to form a wide variety of substances. One that you've heard of is homocysteine. Now, we've all perhaps heard that elevated homocysteine is a marker of vascular disease. This whole cycle is about moving methyl groups. And homocysteine is elevated if you don't have adequate methylation. What happens is homocysteine gets methylated back to methionine. And all methylation means is taking a carbon, which is depicted here with its attendant hydrogens, and moving it around from molecule to molecule. So what we've talked about tonight is going from electrons moving through things, and we didn't touch on protons as much, but it's in there. Protons are actually the hydrogens, and they move in the oxidative phosphorylation inside the mitochondria also. And now we're talking about carbons being moved around. Just to point out the evolution of our discussion on chemistry here. So there's some materials that are formed. The first one is S-adenosyl methionine. We're back to that ADP group. ATP gives off of phosphorus and makes adenosine available, and it becomes methylated, and they call that S-adenosyl methionine, or SAMe. Many of you probably have heard of SAMe. It's popular as a supplement, sometimes used for people with depression and that sort of thing. And then it moves the carbon group to the next material called S-adenosyl homocysteine, and then on to homocysteine. And along this way, from homocysteine comes the cysteine that is used to form glutathione. So that's where my interest first came, and I was aware of this for a while, but didn't realize its importance until the Jill James article came out, or actually prior to that, when I kept hearing about this. Most of us are taught that you can take homocysteine back to normal by giving B12 or folic acid. That should move this back. In children with autism, however, they don't methylate very well, and they have low SAMe, elevated SAH, low homocysteine, by the way, low cysteine and low glutathione. So all of a sudden, a biomarker of autism has become the deficiency of glutathione. Kind of puts it back on my roadmap pretty dramatically. And I think when you look at the mechanisms that are at play, we don't have time to go into all the offshoots that come off of this tonight, but you can account for a lot of the mechanistic problems that you see in children with autism. In fact, there's an article that shows that if you deplete glutathione in infant mice, even for a short period of time, and expose them to stressors which release dopamine, you can have impairment in mouse cognitive function later on. In other words, that small period of time when they were missing the glutathione and they got overstimulated can lead to problems even later in the mouse adult life. And I think that has a lot of implications for this disease state we call autism. So anyway, the article went on to show that just plain old B12 didn't solve things, folic acid didn't solve things. Here's the additional studies. Dr. James pointed out that one interpretation of his findings that children with autism would be less able to detoxify and eliminate heavy metals because there's a strong association with mercury and autism, and it would take a whole different discussion for me to show you the complex mechanisms and the way they interact, but it's becoming more and more obvious once you see these basic, we're looking at the basic premise of glutathione tonight. This is basically what I just told you about, and what she found in her article is that if you give even folinic acid and trimethylglycine and B12, all these things that are supposed to get this methylation cycle working, it doesn't work. And it doesn't work until you give them methylated B12. Makes sense. You need a methyl group. That's what B12 does. It picks up a carbon methyl group, hands it off, picks it up from homocysteine, hands it to methionine. That's one of the major functions of B12. It also shows you how critical B12 is, because when it's not working, you end up with these difficult problems. Well, that's great. Well, how do you make methyl B12? You've got to keep asking these questions. Turns out that to make methyl B12, you need an intermediate step. It just doesn't make, it's not easy to get that methyl group stuck on there. You actually need glutathione. There's an intermediate step called glutathioneal cobalamin. B12 is cobalamin. You need glutathioneal cobalamin. You need to have a glutathione present in order for this whole thing to happen. So, in summary, what happens is, and this is why I think a lot of chronic illnesses perpetuate, is that if you can't make glutathione, you can't run the cycle that makes glutathione. Just like the old expression, you need money to make money, you need glutathione to make glutathione. Let's see, here's the glutathione insertion. Didn't want to leave anything out there visually so you can see this. So what's happening in the management of autism is they're finding that if you give methylcobalamin, you get changes, usually for the better, but the children may go through a period where they're really kind of ragged. I mean, they're difficult to deal with in the first place, and they're really uncontrollable. And I think the issue there is that it's like turning on a car that's been sitting for a long time. A lot of junk is going to spew out. But if you give the glutathione first, you're both activating that system and providing a mechanism to detoxify some of the products of oxidation. A lot of metabolic things, especially the products of neurotransmitters like serotonin and dopamine, when they're broken down, they form aldehyde-like materials that need to be detoxified from glutathione. Steve Fox's famous formula for preventing problems after alcohol ingestion points out to me that it's not the alcohol that's so much the problem. That doesn't make you sick right away. What happens is you get sick when you metabolize the alcohol into the attendant aldehydes, like formaldehyde is an aldehyde. That's not the one you necessarily make, but it has that kind of effect on your brain. It's very damaging. Aldehydes are removed by glutathione. So using that formula will help build your glutathione. That's why it works, and in essence, it's a perfect experimental example of this. So there's more information about this at readysorb.com, and the material is, if you're interested in the liposomal glutathione, it's also available at gshnow.com, which is available to consumers. The ReadySorb site is designed more for healthcare professionals, but it's available, and if you get stuck, call me. We'll figure something out. But it's readily available through these sites. That's all I had planned to talk about. If you want to go a little longer, I can talk about virus and the role of glutathione and take questions. Go ahead in the front.
Do you know anything about the similar relationships with pulmonary sarcoidosis or rheumatoid arthritis?
Well, I can speak. I haven't studied the sarcoid issue. I suspect it's going to fall into one of these categories. The funny thing about arthritis is that it doesn't fall into this chronic inflammation. I mean, it is an example of chronic inflammation, but most people think it's more of the T cells gone wild, if you will, having too much of a reaction. And so what it appears to me is if you have too little T cell function or too much T cell function, you're going to run into problems. In other words, if it's not regulated. So what you want is these things coming back towards the middle. And glutathione is one mechanism that helps regulate both sides of that. And the other part of that equation is vitamin D. And you can get into, are you having someone talking on vitamin D coming up?
No. Periodically we have an expert. I don't know if it's still
Well, vitamin D plays a huge role in calming the T cell excess function, so the combination works very nicely. Yes. I'm sorry. Well, go ahead. You're next. I apologize. Go ahead, sir.
I saw on TV one of these physicians was advocating taking glutathione itself daily. Is it possible to take it? Is it sold?
It is sold, and I apologize for not bringing it up earlier. Thank you. Plain glutathione, neat, without anything added to it, if you will, is available and has been sold in this country for 25 years. There has been little documentation that you see dramatic improvements, such as the ones I illustrated, with plain glutathione. There are anecdotal reports of people using it either sublingually or taking it in capsules and getting improvement. But as I pointed out with the kids with cystic fibrosis, for example, there's not any consistent improvement with those mechanisms. And there's other reasons why, well, I'm going off a little bit, but there's also some studies, it was small, which shows no uptake of glutathione, and I know that from the neat form, and I know that was corroborated by another study that's not published. And so the liposomal form, in my experience so far, has been more reliable, but glutathione is available. It's not hugely expensive, and you can get it in a health food store, and there's nothing wrong in trying it, but I would caution you, you probably ought to, if you're going to do that route, cover your bet by taking NAC also. Steve?
I was going to say that, in my opinion, NAC is probably 2 or 4 times the bang for your buck in terms of antioxidant effect per dollar spent. Glutathione is only has a relatively small amount of the sulfhydryl group on it, which is what binds with mercury and what provides the antioxidant protection. So you get more of that with cysteine or with N-acetylcysteine.
That's true. My experience has been just what you stated with plain neat glutathione. Depending on what the situation is, though, NAC doesn't solve these other kind of acute problems, and that's really where I'm addressing my statements. But for long-term maintenance, I think NAC and glutamine, if you're on a low meat diet, for example, would be a very important way to go. And then with the understanding, and we talked about this in the conference on virus and pandemic preparation, it might be worth viewing on the videotape. The mechanism that's involved with protection against virus is release of a very potent biochemical called tumor necrosis factor, or cachexin, that causes you to feel bad. But it destroys, it increases the oxidation stress of membranes, which is fine because it kills invading bacteria and virus, but you have to upregulate your antioxidant defense to defend your own cell system. And that's where glutathione comes in there. Yes?
From what you said, you could deduce the fact that glutathione, or some form of it, would be beneficial in the case of autoimmune diseases. I'm particularly thinking about one case where the person has vasculitis, and I wondered if any work has been done in this particular type of complaint. If somebody might be able to give me some ideas.
There's actually a double-blinded study that looked at people with vascular disease, small vessel vascular disease, not vasculitis necessarily. But in small vessel vascular disease, in just a week of repeated IV intravenous glutathione, they were able to measure improvement. I think the big problem in seeing glutathione in all the applications clinically, there's almost 68,000 basic science articles on PubMed when you type in glutathione. There's about a dozen clinical articles. In that translation, I think what's been lost is it's been very difficult to stabilize glutathione for IV use. It's expensive, it's not patentable, nobody can promote it, and it just hasn't worked its way. So there's been no reason for anyone to go to the expense of bringing it in as a pharmacologic agent. I think that the improvement seen with the oral liposomal glutathione is heralding a change in that if you get enough glutathione in an easy way orally, you may see dramatic changes in a variety of diseases that are unexplored at this point in time. Your comment about autoimmune disease is appropriate. That does fall under that general umbrella of chronic inflammation. And I think you need more than just glutathione. I think it's a little bit like closing the barn door once the animal is out of the barn, though. When you give glutathione once autoimmune disease has started, you may need some other manipulations to aid in calming it down, but it could be an integral part. And the iodine issue in regard to thyroid, for example, is going to play a big role in some of the most common autoimmune disease that I see is autoimmune thyroiditis, and so the combination of iodine and oral glutathione may prove of great benefit. I've seen one case like that, but I don't know if that was just a fluke or not.
Well, what I'm thinking of is being able to reduce the amount of prednisone that's being used to counteract this.
Well, it's interesting, isn't it? Prednisone suppresses inflammation. And somewhere back in my memory banks, I think it's related to increasing access to glutathione, but I'm not certain about that, so I'm not going to go on record as saying that. But there is some overlap. That would have to be explored. That's a great research project. Oh, if anybody wants to donate for a research project, I've got one ready to go. So, if you've got a check ready, come on up. What's the next question?
What are you recommending or suggesting the dose for liposomal glutathione for aging And what dose would you use, for example, in the acute episode of the flu?
I started out using the IV doses that were published, like for Parkinson's disease, with 600 milligrams, which is a teaspoon and a half of the Redizor glutathione, the way that's constructed. And so twice a day for an acute process. You could use quite a bit more. I've given quite a bit more. I've given 2,500 milligrams at a time to people with acute flu episodes. But usually what I do in that setting is give 400 to 800 milligrams every 1 to 2 hours, just to observe the mechanisms that are happening. And you can sometimes titer people's symptoms. In my clinical experience. Now, none of this has been published, and none of this is, I hasten to add, since the videotape is running, it's been presented to the FDA, and it's not designed to treat any disease. Anecdotally, in my experience, that if you could demonstration, even though it's been around 25 years. And I think that is also one of the examples. Now, if you take oral glutathione and it's helping you, don't stop. I mean, there are individuals in whom it may be beneficial. Well, most people think the plain need glutathione without some mechanism to improve its absorbability is being used up in the GI tract or broken down or something like that. It just doesn't give the systemic kind of changes that you see with IV glutathione, for example.
How about transdermal?
Transdermal is a good route. I haven't heard, I think that the next problem is it's just a matter of volume. How much can you get in? There's nothing wrong with transdermal.
Back to autism, then is it possible then to use the liposomal glutathione and B12 and cobalamin to affect change? You need all three of those?
There have been consistent anecdotal observations of that. There's no formal studies that have been done supporting that. But I work with a pediatrician in Redwood City who's using liposomal glutathione in all his patients. He specializes in autism, and he's using it in all his patients because of the obvious lack of glutathione. And there have been reports, sometimes dramatic, of improvement on that combination.
What relative dosages would those be? And also, may I have a reference to that physician?
David Traver, T-R-A-V-E-R. The dosing is 100 milligrams for every 30 pounds of body weight, once or twice a day. And again, twice a day when you get started. But it really depends on how sensitive the child is, because some of them do better on even tiny amounts, and others you need larger amounts. And what's happening is, the trend is that once you find the tolerated dose, often you need to even give more later. Because you've got a real deficit there. They haven't been making it. They've acquired a lot of toxins. They've got chronic inflammation. All these things are documented in the literature as happening with children with autism, as well as elevated toxic metals.
And then what would be the relative doses of B12 and methylated B12 and cobalamin?
The methylated B12 is, I forget the exact dosing on that. There's some prescription of, based on weight, which you could give 250 micrograms a day without any problem.
Cobalamin?
Well, the methylated form is what I would recommend, yeah. Yeah, you're welcome. Oh, wait, let me go back over here, since, didn't you just have one or something? No, you're up, go ahead. I'm sorry, we'll come back over there. I'm terrible at this
I think I saw a slide that was going to comment on thimerosal, and it didn't last long, and I didn't say anything about it.
Yeah, well, the thimerosal issue is it's an organic form of mercury. Now, the confusing thing is that you'll get lost in the literature of mercury, in people writing about one form of mercury being more dangerous than another. Mercury is dangerous, period. The different forms have to do with how easily they cross into cells and what happens there. And the methyl mercury, so-called organic mercury, ironically, thimerosal is a sulfur combination with mercury, so it's really an organic mercury, and it goes into cells quite readily. And then what happens in the cells is it's transformed into inorganic mercury, and that is disruptive of a number of mechanisms. And that's been a real hot button issue in the autism community, because they have seen their claim is that they see many children normal up to the point where they get certain immunizations. I personally think you could get the same mechanism. The mercury is an obvious oxidizer, and there's any number of reasons why they've kept it in there, ranging from preservative action to perhaps you're confusing the immune system and shunting it over towards this chronic inflammation, and we have used as a measure of immunization an elevation of antibody, and that's what happens with chronic inflammation. You get antibodies raised, and those are the first things we could measure. Looking at T cell function is a more elegant, difficult thing to do, and has only been available in the very recent modern era, yet we've been immunizing for 100 years. So the antibody production was the first thing that was measured, and ironically, they just talked about alum, which is an aluminum precipitate that is, they are looking at it to see if they can increase or lower the dose of influenza vaccine that people would have to take, so they can see a higher level of antibody response. When you put the aluminum in there, you're going to begin to get the same kind of action in the immune cells, so you create this inflammatory response. And I think the question has never been raised, is that the only thing you want to measure and have happen after immunization? But that's the way it's been done. The military there was a study published back in the 80s where they took tetanus toxoid, and they found that they could give a tenth of the dose as a skin test on the arm and get the same antibody response as giving a big injection in the muscle. And they said this has been repeated and it's got statistical validity, but since we've been doing it this way forever, we're going to keep doing it the way we always did it. That was the conclusion of the article.
Wow.
Back here.
On the Parkinson's issue, are there studies that show other metals also stored in the mitochondria? And then the second question is, where is dopamine made in the body? Is it only, did you say it's made in the substantia nigra?
Well, it's probably made in a lot of cells, but the substantia nigra is the primary source for dopamine in the brain.
Okay, is it also made in the adrenals?
Yes, that's the foundation material for adrenaline, which is epinephrine that comes from norepinephrine that comes from dopamine. The largest source of these things, of these neurotransmitters, is the gastrointestinal tract for serotonin and dopamine. And there's a whole recent evolution of thinking. I can't give you a reference right offhand, but it was in maybe even Time magazine about, is this a second brain? Is the gastrointestinal tract a second brain because it's making so much neurotransmitter? The problem is that it doesn't go into the brain itself. The neurotransmitters for the brain have to be made in the brain. What happens in the brain stays in the brain.
Are there studies that show other metals stored?
I don't know. I haven't. I think there's been some studies with lead. I'm not certain, but there have been studies that show that lead's disruptive of many enzyme systems. There was a second part. No, another part. Okay. Oh, and you know what happens with Parkinson's disease is there is an association with I think it's a pesticide material that's used in agriculture. There's a statistical association. There's not a hard cause and effect association. And then you get a lot of oxidized iron piled up inside those cells also. And that could be kind of the oxidizing fuel that keeps the whole thing going, the whole problem going. So it's complex, but it involves antioxidant functioning for sure, glutathione.
Which lab?
I'm not going to let Steve Fox ask me any questions. Now I'm coming back. Go ahead.
Which lab can do an accurate glutathione level?
Well, which lab does glutathione levels?
Yes.
They give reproducible accuracy. The question is it reflective of what's happening? AMSCOT lab is probably the one that's got the most consistent testing. And I think they're now called Midwest Medical Labs. But there's other labs, Immunoscience, and I think Great Smoky's lab also does some form of glutathione testing. And the last question for Steve.
Well, I was asking to ask
question. I was going to comment on the metals.
Oh, go ahead, please.
It appears that in situations where autism is reversed, that there's a dumping of a broad spectrum of metals in the urine as a characteristic, sign of that. Also, in idiopathic cardiomyopathy, where teenagers die of heart failure from mercury poisoning, it's not just mercury that's elevated. Mercury may be, 10,000 times normal, but there's aluminum may be 200 times normal, and cadmium may be 150 times normal, and iron may be 5 times normal. So it appears that a lot of these metal toxicities are generalized incompetence of metal transport mechanisms.
Oh, thank you.
I think that's a big area, and I think you're absolutely right. The mercury is one that seems to be, if you pull that out, you can get the others out too. So that's why I end up focusing on that. And there's a huge literature on it. I guess we have a question. You're the leader.
Let's hold it up. Tim, why don't you talk to Tim? People, listen, everybody. It's been a great meeting, and I wish you all the best of the holidays. And see you again in January. We're gonna have a great speaker.
The only thing you might do